Welcome, Mike here with the famous Monty Hall problem, just a good example of conditional probability. And if you can work through this problem, understand the basic math in the 2x2 tables we're going to show you, you understand how to manipulate all the kind of conditional probability problems we'll see in this class. The Monty Hall problem is made famous because the host of the game show was called Monty Hall. This was in the 70s, I think, so before a lot of people watching this were born. But the idea of the Monty Hall on Let's Make a Deal was the name of the game show, where there are 3 doors. And there's 1 prize or 2 blanks. Or often there's a goat behind one of the doors. So this picture here doesn't exactly go in with what's going on with the game. But the idea is that there's a prize and behind one door and 2 of the other doors are empty. And the showmaster, of course, Monty Hall, knows where the prize is, knows which doors are empty, and that's a big assumption that you have to know about. What happens is that the contestant chooses a door, and there's a 1/3 chance that the contestant wins, that the contestant chose the correct door, because there's 1 winning door and 2 losing doors. The game master then opens an empty door. He's not going to open the door with the prize, of course, but the game master opens an empty door. There always will be at least 1 empty door he can open. Now there are 2 doors left. And the question is, do you want to switch or do you not want to switch? And people think, well, there's 2 doors left. It's a 50-50, so it doesn't matter if I switch or if I do switch. But actually it does matter. And the probability you win is greater if you actually switch. And it confuses people a lot. And it's a whole conditional probability issue. And we'll go through the math right now and work through the conditional probability. It's a very famous problem. This is Kevin Spacey from the movie 21. And you can look at YouTube on this, and he goes through it in this classroom setting. So there's 2 different scenarios. One is if your strategy is to switch doors. The other is if your strategy is to never switch doors. So this is the strategy where you always switch doors. We define 2 events. A is you choose the winning door at the beginning. W is to win the prize, and you switch doors. So if you choose the door at the beginning, let's see why this is 0. Let's understand the strategy is you always switch doors. If you choose the winning door at the beginning, but your strategy is you always switch, the probability you win is going to be 0. Now, of course, the probability you choose the winning door is 1/3. The probability you don't choose the winning door is 2/3. So these are always the same. But under this strategy, remember there are only 2 doors remaining. If you chose the winning door at the beginning and you switch, the probability you win is going to be 0. If you don't choose the winning door at the beginning, that's a bar, and you switch, the probability you win is going to be 1. So this is the information we know. What do we want to find? We want to find the probability you win, the overall probability you win. What are events? W and A. So this is going to be, let's call this A bar. This is W. This is W bar. What do we know? We know A is 1/3, A bar is 2/3. This is 1/3. This is 2/3. Now we know W given A is 0, and that means W and A is going to be 0. So W and A is going to be 0. If that's 0, this has to be 1/3. We have that so far. W given A bar equals 1. So let's look at this one. Probability of W given A bar equals 1 equals the probability of W and A bar. Now what's the probability of A bar? That's 2/3 divided by 2/3. So this tells me that the probability of W and A bar is 2/3. So I get 2/3. This has to be 0 because adding across has to be 0. And I get the answers. So this says the probability of W, just going to add down this way. The probability of W is going to be 2/3. What does this tell me? This says that if my strategy is to always switch doors, the probability I win overall is 2/3 of the time. So 2/3 of the time, I'm going to win. It seems like a good strategy to do. Now let's try the other strategy. This is you do not switch doors. Again, this stuff is exactly the same probabilities as before. Under the strategy where you do not switch doors, if you chose the winning door at the beginning, the probability you win is 1 because you're never going to switch. If you don't choose the winning doors at the beginning, the probability you win is going to be 0 because you don't switch. Well, let's do this again. A bar, this is 1/3, this is 2/3, This is W bar. Now I know W and A bar is going to be 0 from there, so W and A bar is going to be 0. This has to be 2/3. Now I got to fill in the top there. So W given A is 1. So the probability of W given A equals 1 equals the probability of W and A over the probability of A. It's going to be 1. So W and A is going to be 1/3. So this is 1/3. This has to be 0 because adding across gives you 1/3. This equals 1/3. So what's the best strategy? Should you always switch or never switch? Recap, we just did this. If your strategy is to always switch doors, the probability of win is 2/3. If your strategy is to never switch doors, the probability of win is 1/3. So the best strategy is to always switch. It's bizarre, but the best strategy is to always switch. According to the New York Times, this problem was debated. So Marilyn von Savant has the, I think it's either the American or the world record for IQ, the highest IQ in the world, or at least in America. And she used to have a column in Parade magazine where she wrote up a solution to this. And it was a very controversial solution because she gave the correct answer. She said you should always switch. And the New York Times wrote about this because there was a lot of mail that was sent in after Marilyn von Savant wrote this column. And many people said, you blew it big, and didn't really understand conditioning, didn't understand conditional probability. It's a very confusing problem for a lot of people. What's interesting is that Percy Diaconis, who used to work at Harvard, he's actually Joe Blitzstein, who teaches the amazing 110 probability course and wrote a book on probability. Percy Diaconis was Joe's PhD advisor at Stanford. And what's nice about this is that, and I highlighted, our brains are just not wired to do probability problems very well. If you don't have intuition about this, don't worry. It's difficult. That's why we run through the math. That's why we work through 2x2 tables. But a lot of these problems are not obvious at the get-go. Our brains are not wired to understand this. We have heuristics we want to use that are not always correct. So that's the famous Monty Hall problem. Hopefully it gives you a little to work on. Great practice on just making sure you understand a 2x2 table. Hope you're having a great day, and we'll see you in class soon.